Okay, so this page we are going to look at turning points of our different polynomial graphs. This will be how many times your graph changes direction. So we're going to look at a couple sketches, identify the number of turning points, and then we'll kind of look at the correlation between some of these polynomials and their turning points. So to start off, just do a nice linear function. I think on the last page we did a negative slope, so let's just do a positive slope. But as you can see, a linear function is a line. Okay, no matter if it has a positive or negative slope, it has 0 turning points. It never changes direction. And that's going to be true pretty much for every linear function because it gives you that line shape. Okay, so pretty straightforward, nothing too crazy there. So as we go over to quadratic, a quadratic, remember, gives us that parabola U shape. So, all right, it can open up or down. Let's just open up. Okay, but as I have my parabola, all right, just kind of a random example, you see that it changes directions once. Okay, so like in my example, I go down and then it shifts and then goes up, okay? Obviously, if it closed down, it would kind of do the same thing. It'd go up and then shift down, okay? So it has one turning point right there at the vertex. And like I said, kind of similar to linear, quadratics will always kind of follow this idea. So one turning point. Now, the last two we're going to look at, cubic and quartic, okay, are a little different, a little interesting, okay? But for cubic, it is actually possible that a cubic has 0 turning points or 2. So, what I did was I put into Desmos, okay, kind of 2 cubic functions. Look, x cubed minus 3x squared, and the bottom one, 3x cubed plus 18x squared plus 36x plus 24. Both cubics, because look at their degree, highest exponent is 3, okay? But as you look at this graph here, okay, and it's kind of glitching out on me, but we can see it right here, okay? This green function right here on the left side, look, it does not have any turning points. So even though it comes up, okay, right about at that -2 there, okay, it kind of flat lines a little bit, but it doesn't change direction and come back down. It continues to go back up. Whereas the blue function, you can kind of clearly see it changes direction twice, all right, a big kind of wavy curves right there. All right, so that's kind of the 2 examples I'm going to draw over here. They're both cubics, but one of them is going to kind of come up and flatline, but then shoot back up. So it doesn't actually change direction at all, but still has that cubic shape. Whereas you can also have a cubic function that does come back up, shoot back down, and then back up. Okay, that kind of has 2 turning points. All right, so a little interesting there. Most of them are probably going to have 2 turning points for a cubic, but it is possible you can have some that have 0, kind of like the parent function. So a quartic is going to be kind of similar, where there's actually quartics that only have 1 turning point. Now, we're not going to do too much with them. They sometimes kind of look like parabolas, where they kind of flatten out and go here, okay? So they can have 1 turning point. Like I said, we're not going to do too much with those. Most of the quartics that we look at are going to have 3, or they're going to look like this. So maybe I had the first one opening up down. Let's open this one back up. So look, it's going to go 1 turning point, 2 turning point, 3 turning point. And if you think about end behavior that we looked at in the previous lesson, okay, if you look at end behavior, remember a quartic polynomial, all right, is an even degree, so your end behavior, your arrow should be going in the same direction. So that's what's happening here for both of these. Okay, so that kind of takes a look at some of the turning points for these graphs. All right, so to finish up the notes real quick, and then we'll just kind of finish up with some examples, all right? I'm going to kind of add in our note here. So the note that I'm going to add is we're going to say the maximum. So notice how I capitalized all that. Maximum is going to be a really important word. Maximum number of turning points is, and then there's something special that we're going to connect. So coming back out to, okay, I might actually give myself a little more room here. I didn't realize I had more room. Okay, so if you look at all these problems, all right, a linear function has a degree of 1, and we had 0 maximum turning points. All right, there's only one option. And look, degree of 2 for a quadratic had 1 turning point. Now, cubic and quartic, I kind of showed you 2 examples of number of turning points you could have. But once again, that's why I underlined this word maximum right here. Okay, the maximum amount of turning points that you can have for a cubic is 2. Okay, so degree of 3 and 2. And the maximum amount of turning points you can have for a quartic is 3. Degree of 4, 3 maximum turning points. So what do you notice about all those ones that I underlined in red is that, take a look, if you have your degree and you subtract 1 away, you get the maximum number of turning points. So the maximum number of turning points is your degree minus 1. Now once again, does that give you the exact number of turning points? No, it is possible your cubic has 0, your quartic has 1, okay, but it is the maximum number of possible ones that you can have. So to finish up this page, given the graph, determine the end behavior, number of roots, and the number of turning points. So, number of roots. Now, guys, when you're looking at the number of roots from a graph, all right, you can probably get the number of possible roots if you can identify what degree your graph is. But if you have the picture of a graph, sometimes they'll ask for a number of real roots. So maybe let's do that here, because our practice is going to kind of do that. So let's just look at number of real roots, which, reminder, is also x-intercepts. So look, how many x-intercepts, number of real roots do I have? This would be 3 for this one. Okay, and let's just go down the list. Let's do them all at the same time. 1, 2, 3 for that one. And here we have 2. Okay. So there's the number of real roots. Now, before I move on, I want to talk about one thing about roots, okay? On the last page of notes in the roots notes section, we said that the number of roots is equal to the degree, okay? Now, look at these 2 functions real quick. I just said that these have 3 real roots, 3 real roots, but you can kind of see just by end behavior alone, look, those arrows go in different directions. These arrows are going in the same direction. I know that these 2 functions are not the same degree. So that kind of shows me that not all these roots are real necessarily. But we're just looking at real roots right now, the x-intercept. So the number of turning points, remember, is the number of time to change direction. So that would be right here. Actually, let's change up color here. There's a turning point. There's a turning point. 2. Okay, and then how do I know this second one's not a cubic? Because look, how many turning points? 1, 2, 3. A cubic cannot have 3 turning points because the maximum amount is degree minus 1. And then our last one here, look, parabola, 1 turning point. Okay, so to finish this problem, we're going to end with end behavior. Okay, end behavior. So quick reminder about end behavior is, reminder, x arrow negative infinity means as x approaches negative infinity, it's a fancy math way of saying left. Okay, and then remember, this bottom one's a fancy math way of saying right as x approaches positive infinity. So the y's mean that I am looking at what are my arrows doing up and down. So as I go to the left, my arrow is going down to negative infinity. And look, my other arrow is going the opposite direction. So right away, I already know that that one is going to positive infinity, 1 of each. And look at that shape. That is a cubic function. Okay, cubic functions are odd, so they should be going in both directions. So as I go to my second one, same thing. This is left, this is right, if you want to add that in. But look, I actually don't really have to pay attention to left and right because both of my arrows are going down. So regardless of if I'm going left or right, they're both going down, negative infinity, negative infinity. They both go down towards negative infinity. And guess what? All right, I know I said the number of real roots is 3, but with the number of turning points and this end behavior going on here, okay, I can kind of see that this is a quartic polynomial. So, all right, we identified that this one's cubic based on the shape and some other information. This one is actually going to be a quartic. And remember, quartic is an even degree polynomial, so my arrow should be going in the same direction. So our last one here, we have a parabola, same deal. Now I know the arrows are cut off because we got this from Desmos, but my arrows would be up here. Look, if they're both shooting up, then yeah, I can identify left and right, that's fine, but I'll be honest, if they're both going up, they're both going up to infinity. Okay, and then same thing with all of my information I have, this is a quadratic. Okay, it's an even degree polynomial, they're both going the same direction. There's how we can identify some of our roots, turning points, and end behavior. Kind of the three things that we looked at in this lesson too. Cool?